All right. Good afternoon, everyone. Thank you for coming on this super cold day. We have a presentation by Dr. Shai Genel today, who obtained his PhD at the Max Planck Institute in Germany, and then he held a Hubble Fellowship in Harvard. And for a few years now, he's been at the Center for Computational Astrophysics, which is an institute in New York City, which specializes in bringing people together to tackle really difficult problems, which are hard to solve in one small place. And this is a super active place with lots of visitors and lots of stuff. And if you're interested, you can probably ask Shai, maybe at the end, at the question session. They also bring a lot of visitors that you can come and participate and collaborate. So if you're interested in any of the topics that you hear today, maybe there's an opportunity to work with Shai. But what he's been famous for is tackling really difficult problems in detailed modeling of how cosmic gas turns into stars, essentially, and eventually black holes. And there are a lot of complicated details that are involved in that nonlinear three-dimensional, very high-resolution modeling. And he's been tackling several of these problems over time. And now, not only doing the pure hydrodynamics, now he has added the addition of machine learning techniques to try to do it more efficiently and really probe that very, very complex nonlinear problem. So we're happy to have Shai talk about this, and here's you.
Great, thank you very much, Alex. Thank you all for coming here this afternoon. So yeah. Indeed, I will talk about my work and with many collaborators over the past few years on how we can connect what I just mentioned, modeling of galaxies, of galaxy formation, of cosmic gas, to cosmology, actually, to inferences about the fundamental properties of our universe with the help of machine learning. So I'll start with a brief outline to orient you. So I'm going to start with some introductions. Oh, the pointer isn't working. Oh, it's there. Okay, sorry. Okay, so I'll start with a bit of introduction to how cosmology and galaxy formation actually kind of intersect in what I call the small scales of the large scale structure of the universe. I'll explain a bit what I mean by that. And then a little bit about cosmological simulation, which is our main tool for modeling galaxy evolution and the complex structure formation process in the universe. Then I'll jump into kind of the results, and I'll start by outlining the basic methodology for this project that I'll be talking about. Essentially, how we approach marginalizing over our uncertainty in how to model the physics of galaxy formation, and then talk about three specific ways we are, or specific observables that we are targeting and trying to make inference using for cosmology. And I'll end up with an outlook and summary. Okay, so starting with how cosmology and galaxy formation intersect in the small scales of the large scale structure. So generally, how do we hope to constrain the cosmological parameters of the universe? So for example, how much dark matter there is, what is the expansion rate of the universe, what is the equation of state of dark energy or primordial non-Gaussianity, and things like this. So generally, we have the very large scales and the very early times, which we see in the cosmic microwave background. And then we have more nearby objects, namely galaxies, and how they distribute in space. So that's a probe of late time and smaller scales. So CMB has provided us with very, essentially a revolution in the past couple of decades in terms of measurement of these basic properties of the universe. But there's a limit essentially to how much information we can extract out of it, because we only see these linear scales. In the local universe, at these small scales, which are actually nonlinear and very evolved by many complicated processes, there's much more information, but the difficulty is in extracting that information. Now, in the upcoming decade, there's going to be many new surveys, galaxy surveys, that will probe this kind of late time, small-scale regime. But the challenge is how to extract this information from this late time small scale regime. Because the processes that govern that regime are nonlinear, and the observations are non-Gaussian, and so on. Moreover, those scales and those times are affected specifically by what we call baryonic physics. This is the physics of the normal matter in the universe. This is the physics that govern supernova explosions, or even the conversion of cosmic gas into stars, what happens around black holes, all these things that we don't yet really understand very well, and we definitely cannot model in our large-scale simulations because they occur on such small scales. However, they do affect the larger scales of, like, say, 1 or 10 megaparsec scales, from which we hope to extract this information. So we somehow need to know about or model these small scale processes that we don't fully understand, because they really their effects propagate into much larger scales from which we want to extract information. So this is just a demonstration with a very simple model, how the power spectrum as a function of k, wave number, is affected, as the power spectrum is suppressed by these effects of baryonic physics, and for different assumptions simple assumptions about the baryonic physics. So and this is just a demonstration that if this is ignored or modeled incorrectly, this can actually bias the inference on cosmological parameters. So these are some of the famous cosmological parameters we're interested in. So this sigma 8 essentially measures how much fluctuation of matter there is in the universe, and omega matter is the content of the universe in terms of matter versus energy. And these various contours, various kind of reddish contours, show different constraints that one gets by different modeling of those small scale physics. So we see that there are biases here that are comparable to the total tight constraint that we get from the CMB. So essentially, we want to shrink these things down to this scale, and also make them robust to this baryonic modeling. Okay, so how do we model these complicated nonlinear late-time processes? We do this using cosmological simulations. Cosmological here means that these are simulations that start from cosmologically motivated initial conditions, namely from the early universe, for something like this, the cosmic microwave background, even if not exactly. And then from these initial conditions, we essentially follow as much physics as we can and evolve these kind of mini universes down to the present day, down to redshift 0. So what do we usually include in these simulations? We have cold dark matter and baryons, normal matter. These are the main components of the universe. These are put in an expanding universe that essentially within it we have Newtonian gravity. That's enough, good enough approximation for this scale. The expanding universe, of course, comes from GR. Then the dark matter, the cold dark matter, is collisionless, so it only feels the forces of gravity. But the cosmic gas, the normal matter, is modeled with essentially, let's say in the vanilla case, ideal hydrodynamics. And we follow the basic components of normal matter: hydrogen, helium, and more heavy elements, which we call metals. Then we have some optically thin radiative cooling, which is important for how galaxies form, which I'll touch on in the next slide, and some basic chemical equations for the ionization structure of the gas. So this is the standard, and what does this get us? This actually gets us pretty far. This gets us to galaxies. So let's see how that looks like. So on the left here, we see the process of gravitational instability on very large scales of the universe, which leads to structure formation. So we start with an almost uniform universe coming out of the cosmic microwave background. And over time, structures collapse under, the overdense structures become more and more dense, and we get this formation of what we call the cosmic web. This is the large scale structure of the universe. The small scale, what I call the small scales of the large scale structure, are these little things here, which are dark matter halos, inside of which galaxies form. So if we now zoom in onto one of these halos, now we see the gas, not only dark matter. Now we have all these hydrodynamic processes, and we see gas essentially flowing down, cooling to the center of the dark matter halo's potential well. And when it becomes dense enough, it forms stars, and this is then we get galaxies. So it's nice that with actually very simple, robust components, we get galaxies. We get kind of wrong galaxies. They don't really look like real galaxies. For this, we need more stuff. So before I touch in some more detail about what that more stuff is, just want to kind of get everyone on the same page in terms of where we are in kind of what these simulations are able to do these days. So I would say that in the past decade or so, there was a revolution in what these simulations can do. Now we can follow fairly large cosmological volumes, still much smaller than the observable universe, but we're talking about hundreds of megaparsec, in which we have tens of thousands of galaxies that are forming. Each of those are even starting to be marginally spatially resolved. And so these are examples for simulated galaxies with comparison to the real Sombrero galaxy. So you can see they start looking, the resolution is not quite there yet, but they're starting to look like real galaxies. And this wasn't the case a few years ago. And these are very big computational efforts on the order of tens of millions of CPU hours and petabytes of data. So, and generally speaking, there are a few groups, a handful or maybe 10 or there are 10 groups around the world who develop these kind of codes and these kind of galaxy formation models. These are examples of these. And so we now live in a world where we have this kind of a few sandboxes that everyone is using and analyzing to try to understand how did the galaxies actually form in these simulations. So what else is needed in these simulations to get the galaxies, so to say, right? So you may want to add some warm or hot dark matter because we don't know for sure that dark matter is only cold. You may want to add cosmic rays, dust, magnetic fields, or more serious modeling of the radiation beyond just optically thin. Then you could add non-ideal hydrodynamic effects, radiation, hydrodynamics, I mentioned, non-equilibrium chemistry, and and the effects of magnetohydrodynamics. So different groups are starting to do these different things to different degrees. The main elephant in the room still is what we call feedback, and specifically subgrid models to model those additional processes that I mentioned before. How do stars, under what conditions stars actually form? What happens when stars explode? What happens when black holes accrete material? How do they affect their surrounding? And we think these are actually very important things which are not resolved. So we develop what we call subgrid models to include them in these simulations. And different groups develop these subgrid models in different ways. Usually they're pretty ad hoc, pretty coarse at this point, if we want to be honest. Just to give you a flavor for what that might look like. So this is the radius of like one of those dark matter halos. Here we're showing just the density of gas in the halo. This is exactly the same halo with the same initial conditions once evolved without these feedback processes and once with. So you can see that they affect very importantly the whole structure of the gas in the halo, and that the same holds for the properties of the central galaxy that sits at the center here as well. Okay, so I said that there are many groups around the world, or a few groups around the world developing these models, and that we don't really understand the physics that goes into these subgrid models. So the question is now, okay, so if we want to make inferences about cosmology, and these small scale processes affect the larger medium scales that we want to extract information from, how do we account for this uncertainty in how to model these complicated processes? So the answer that me and my colleagues have been taking, or the approach we've been taking in the last few years, is to just marginalize, not wait maybe a few more decades until we know how to model or can model these processes correctly. But for now, for the time being, we have to marginalize over our uncertainty of how to do this modeling. So I'll describe now how we do this. So this is where the CANOS project comes in. So CANOS stands for Cosmology and Astrophysics with Machine Learning Simulations. We currently have a public data set that's been public for about 2 years now. So it's been like a 4 or 5 years old project. It keeps growing, as I'll describe. So what we have now is 3,000 unique cosmological boxes of scale of about 30 megaparsec cube. each of those 3,000 simulations are based on 3 different galaxy formation models. I'll name them because these names will come up again. So TNG, Simba, and Astri. These are just 3 of those kind of different models that have been developed over the past decade or so. So for each of those models, we have 1,000 variations. So not only we use the 3 different models, for each of those models, we vary a range of parameters that control how the model behaves. So we vary 2 cosmological parameters. These are the things that really we're after. We want to be able to extract the information and measure. So omega matter and sigma 8, I mentioned those before. And then we have 4 astrophysical parameters or subgrid parameters that control these complicated unresolved processes. So we have this 6-dimensional parameter space of these 4 parameters, and we sample it kind of semi-randomly with 1,000 points for each of those 3 models. In the meantime, you could see here just examples of some of these boxes. Each box is different, and you can see that the TNG and Simba boxes, if you squint a little bit on those scales, you can see that they're different from one another. So yeah, as I mentioned, this data is public, has been public for some time, and we keep, actually, I hope at the end of this month, or maybe in 2 or 3 weeks, we'll make another pretty major data release of new simulations that I'll describe just a little bit later. So I invite everyone who's interested or thinks that might be useful for them to just go to our website and access the data. Okay, so just before going into applications, I want to describe a little bit more what the simulations look like. So first of all, indeed, what I show here on the lower left is the performance of these 3 different fiducial models, no variations yet. And for 2 randomly selected observables, like the black hole mass function, and again, this suppression of the power spectrum with as a result of the inclusion of the baryons. And what you can see in these solid lines is that each of these 3 models in 3 different colors gives a different answer to these things. And in the shaded regions show you the range of all these 1,000 variations around each model. So you can see also the ranges differ between the models. What we can also do is for each of those models, just take each of those 6 parameters that we vary and just vary each of those 1 at a time. So keep all the 5 fixed and just change 1 at a time. And results are shown here. And again, so 6 panels, 1 for each parameter, 3 colors, 1 for each model. And again, you get the idea that the 3 models, even if you change kind of the same parameter that is supposed to represent the same kind of physics, you get different responses for any number of any kind of observable, so to say, that we can measure out of the simulation. So bottom line, the models are different from one another, which is the whole point. Okay. Beyond that public data release that I just described, I want to just describe quickly something that, one of the data sets that we intend to release in the next few weeks. So we took one of those 3 models, the TNG model, and expanded significantly the parameter space. So instead of just varying these 6 parameters that I mentioned, now we're going to vary almost all the parameters we could find. So 28 parameters. Now these include now 5 cosmological parameters, not only 2. So now we vary the omega baryon, the density of baryons in the universe, the Hubble rate, expansion rate of the universe, and more, and 23 subgrid parameters for the baryonic physics. And so we get somewhat larger range if we just look at the overall percentiles of the distribution of some observable. It widens up when we vary 28 parameters rather than 6 parameters. Importantly, as I'll show later, things still work even in this large dimensional parameter space. And this is again just to demonstrate that we can take each of those 28 parameters separately and just increase or decrease its value, and we can look at the response, for example, at the formation efficiency of stars or of galaxies, and you can see that each parameter has its own quirks. It behaves a little differently, so they're generally not degenerate with one another. Even if you look at one particular observable, you might think, okay, these two behave the same. Once you open it up to more observables, each parameter does a different thing to the model. Okay, so any questions so far before I jump into a few applications and results? Okay. Cool. So, okay, so I'd like to tell you a bit about how we can actually use these simulations to essentially do a demonstration, proof of principle that information indeed can be extracted from these small galactic-like scales, information about these cosmological parameters, even under the influence of all these feedback baryonic processes. So what we do, we took these 3,000 simulations, and we generated many, many tens of thousands of maps from them. So we took each simulation, we sliced it up into 5 slices from different viewing angles, so 15 slices overall. And then we look at different, just create these projected maps of some quantities in simulations. For example, this shows maps of just gas density, distribution of gas. These are maps of the gas phase, so the IGN, the intergalactic gas, essentially. Abundance ratio of two particular elements, magnesium over iron ratio. The galaxy formation people here know why I chose these, but essentially, yeah, some maps that essentially probably look, people who are in this field probably would recognize these kind of maps, probably not so much these kind of maps. It's not something that we can directly observe, but yeah, this is what it looks like. And we're going to try to train machines to look at maps like that and tell us, okay, what was the omega matter value of the simulation that produced this map? This is going to be the exercise. So indeed, so we use convolutional neural networks and train on many of these maps, and it works. So based on these maps of the gas density, if we focus for a moment on the omega matter parameter that I mentioned, so we just have a plot of prediction versus ground truth for maps from the test set, from maps that the CNN has never seen before. And this works amazingly well. So we can constrain omega matter from these maps to a few percent accuracy. Also works pretty well for sigma 8. And to varying degree for these 4 subgrid parameters. For some of them, not so much. For some, yeah, there is some information. So now we can summarize each of these kinds of panels by essentially percent, accuracy over all values of the parameter, and then show it here for different types of maps. So this would be the results, accuracy on the inference of the value of the parameter from these gas mass density gas mass maps, and but also pressure, temperature of the gas, velocity of the gas, magnetic field, and so on. And the different colors are for different parameters. So you can see that certain maps can constrain certain parameters a little better or a little worse. Some maps are not so useful, don't give very high accuracy. Some parameters cannot be inferred very, very well, but the cosmological parameters generally can be inferred to a few percent accuracy. When we add up and train a machine or a CNN that looks at, kind of has several channels, essentially sees all of those quantities, all of those maps, we can get down to to accuracy of like 2 or 3%. On these cosmological parameters, which is really competitive. Now, of course, we can't yet directly observe these kind of maps, so we can't just feed now the real universe into this machine and get the true value of these parameters for the real universe yet. But this is the direction we're trying to go in. Okay, an important point that is that this was based on this TNG model, one of those codes, but the results so far generally are not robust, meaning that if we train a CNN on many maps taken from this TNG model and its variations, then we show it a map generated from one of those SIMBA simulations, the results instead of this look like this. Okay, so it's totally wrong. It doesn't know that it's wrong. Even the error bars are so small. It's just never. So it's like it's never seen anything like that. So and that makes sense. So this is an example again of the same box, the same cosmological volume simulated with the TNG model and with the SIMBA model. This is the temperature of the intergalactic gas. You can see that the fiducial models give very different results. So if you've only been trained on this and you suddenly see this, you'd get very confused. So this is really important because none of these models is correct, is the real physics yet. So we have to be able to get to the point where we show it the real universe and it still gives us an unbiased answer. A nice thing that came out in this study, so the temperature results from the temperature maps was really, really bad in terms of robustness, but the total mass map, just projected mass along the line of sight, actually gave robust results. So we're really happy also because total mass is something that we can imagine is maybe a bit measurable, like it can be measured with gravitational lensing. Again, not exactly, but kind of closely related to that. So we thought that was great. But that was with just two models, the first two models that we ran, TNG and SIMBA. Now we added this third asteroid model, and it doesn't work anymore. So it works even with this total mass maps. So asteroid gets very biased results for sigma 8. Omega matter still works actually pretty well. So that shows you the limit that even if you train on two models, the third model will not necessarily work. These models are different from one another. You do, however, get a little bit improvement simply by training on two models rather than train on one. So this is, again, one of those kind of prediction versus true plots where it's tested on asteroid maps, but different colors show you different training, the machines that have been trained on different sets. So the orange points comes from CNN that has been trained on SIMBA simulations, then tested on asteroid. Okay, so it gets it completely wrong. The green points have been trained on TNG and tested on asteroid. They're like completely outside of the plot, very wrong. The black ones have been trained on both together, just throwing maps from both TNG and SIMBA, then tested on asteroid. Okay, it's in the ballpark. I mean, obviously very bad constraints, but it shows you that simply by training on two models, you get something, but we need to do something more sophisticated than that. Okay, so one direction we're trying to move in is expanding the model space, simulating more and more models, and I'll touch on this a little bit later. Another direction is to actually try to improve train in a different way, train with the goal in mind to increase the robustness. So one approach we're trying now is the following. So instead of just throwing these maps onto a CNN, we use some encoder, namely we compress the information down to some latent space, some small latent space. And then we do the inference directly from those latent variables rather than directly from the map. What does this do? It allows us to add another term to the loss function that essentially tries to make the latent variables contain as much information about the final cosmological parameters. That's what we want to infer, but forget as much information as possible about the actual original data. This is because the original data looks so different. These maps look so different between the different models. So we're trying, so by essentially tweaking the loss function, we can kind of penalize the network for learning specific features in the map, but still ask it to retain information about the final thing that we want to infer, which is the cosmological parameters. We added another layer to this loss function, which is a classifier. So we also try to directly build the classifier between TNG and SIMBA based on those latent variables, and again penalize the network for being able to classify. So yes, okay. So this brings us somewhere, but it's work in progress. So this is some example, again, trained on both TNG and Simba, tested on Astrid for omega matter and for sigma 8, pretty bad. And then with this more involved loss function, we get some improvement, but it's still not there. So yeah, so this is where we come to, okay, we're trying to keep pushing this direction, but also want to expand the parameter space. So what we have now, all we can do now is essentially train on 2 models and test on a third. What if we encompass some very high dimensional space of all the possible galaxy formation models? What if we sample it in more places? What if we try to cover as much of it? Will we eventually cover or get close enough to covering the real physics of the real universe such that results will be robust for real observations? So that's kind of the game we're playing. Now the comment, so I mentioned this new suite of simulation with where we vary 28 parameters. So just want to point out that we were really happy and, I mean, potentially surprised to realize that this kind of exercise still works in this 28-dimensional space. So just to clarify, now we're sampling a 28-dimensional space with only 1,000 sampling points. So every point is very far away from any other point. So we weren't sure at all that a CNN would be able to generalize just from 1,000 samples. But it works pretty well. So this is a comparison of the inference again. So we're back to just working within the TNG framework, no other model. So everything is robust now. This is the kind of inference we could get that I showed before. We could get with varying only 6 parameters, and this is what we get with varying the 28 parameters. So it's pretty comparable. And now we can see that actually we can check, for example, from temperature maps, what are the parameters, the 28 parameters that we can constrain. And yeah, we're really happy also to find that it's mostly the cosmological parameters that are in this part of the plot, where the correlation function between correlation coefficient between inferred and true value are high. So this is what omega matter looks like. This is what NS, the spectral index of the initial conditions, is here. This is what that looks like. So that was really came out of nowhere and made us really happy. All right, and yeah, and now we can play a bit and see like which parameters are best constrained by which kind of maps. And again, generally speaking, it's we get good constraints, better constraints on the cosmological parameters. All right, so I'll switch gears and talk about the second application. And this is about, so no more CNNs. Now inferring again, cosmological parameters, model parameters, from the properties of single individual galaxies, which is also a big surprise for us. So just start by describing the basic result and then getting into a bit more what it means. So essentially, we found that a very simple neural network, fully connected network, can be trained to infer the value of omega matter to about 10% accuracy. So maybe not amazing, but something, from the properties of any individual galaxy in the simulation. So we ran these 1,000 simulations. We have overall millions of galaxies in them. We take any galaxy, we measure some basic properties for it. Its physical size, its mass, its metal enrichment, velocity of the rotation. And we just feed a vector like that of 11 physical properties into this simple neural network and train it to spit out the value of omega matter. And again, it works really nicely. So, and again, to emphasize, this is from any galaxy. So just from any galaxy we pick, these are 3 panels from 3 different simulations with different values of this parameter, omega matter, and see whether it's low, medium, or high. Every galaxy in the simulation gets it pretty close. So that was a real surprise for us, and it took us some time to think what this means, how come this it comes about like that. And the interpretation we came up with is that galaxies in this 11-dimensional space of their physical properties sit on some very thin manifold that we don't know exactly how to describe. And that manifold shifts around as the value of omega matter changes. So it's enough if you have one point, you know on which manifold you are. So that's the interpretation. And the next few slides, I'll try to drill in a little bit and kind of try to confirm if this interpretation is right. Just a comment, though, again, to be clear, that we have the robustness issue. This manifold is just some three-dimensional space of galaxy properties. This manifold, to the extent that we can, visualize it, we'll pick three of those quantities, is different between TNG and Simba. And then, indeed, as you might expect, if you train a machine on these TNG galaxies and then you show it a Simba galaxy, it does not get things right. Okay, so yeah, so as I said, we believe that this manifold shifts with omega matter more than it shifts with other parameters, and that's why we can get an inference on the sigma on the omega matter. But you could also imagine if we have this 11-dimensional space, there's enough freedom for this manifold to also be shifting in a different direction due to some other parameter. And so you could imagine in principle that you would be able to get a constraint on many different model parameters, because every point will tell you exactly the combination of parameters, because there's only one combination of parameters that will move the manifold to include that point. But it doesn't work exactly like that. So yeah, we get these nice constraints on omega matter, some constraints on one of the supernova feedback parameters, but very little for the other parameters. So perhaps interpretation again is that the manifold may not be shifting so much in response to the other parameters. Perhaps we know that varying the values of those other parameters changes the properties of galaxies, but perhaps they just shift up and down, or along the manifold that is defined by the value of omega matter. However, if we add more galaxies, namely do exactly the same thing, but from the properties of 5 galaxies or 10 galaxies, we do actually start getting very tight constraints on some of the other parameters, for example, the supernova feedback parameter. So, and this here, you just see how the RMS drops as we increase the number of galaxies. So potentially, the manifold does actually shift in response to this feedback parameter, but just less. So not by much. And there is some intrinsic scatter to the manifold. So just if you have just one galaxy, you don't know if you're still within the scatter of the original manifold. You don't know that your manifold has shifted. But if you have 10 galaxies, you're essentially able to average them, and you get a very precise positioning on the manifold, and then you know that it's a slightly offset manifold. And we tried then to be even more explicit in this kind of and probe this interpretation of the manifold by using essentially an autoencoder, which is a dimensionality reduction technique, to try to see if we can actually represent that manifold with just a small number of parameters of latent variables. So specifically, we use this kind of new technology that came out by one of our colleagues, Matt Ho, just last year, which is called the information ordered bottleneck approach to autoencoders, in which during the training, essentially you have the ability to open or close the channels, where each channel here is one of the is a latent dimension, is one of the variables that contains this encoding. And the loss function then in the training is constructed such that the network is motivated to essentially put as much information as it can in the channel that is open the most frequently. And so you get this information ordered. So it's in a sense, it's a generalization of PCA. It's a very nonlinear PCA, right? It's a kind of neural network-based PCA, where you get the first component is like the most important component, contains the most information, and then it's sorted, in decreasing amounts of information. And so in one training, you get this. I mean, you could do something similar to that by training separate autoencoders, once with just one latent dimension, then with 2 latent dimensions, then with 3 latent dimensions. You get something similar, but this you get with just one training, and they're stable. So you can then, after training, you can open or close the channels as you wish. And yeah, so then we can look at the correlations of these latent variables with the original physical properties, these properties of the galaxies that I mentioned before. And indeed, we see how the first ones, the top ones, are more strongly correlated. And then we kind of lose the correlations as we get to the 5th or 6th latent dimension, which again, we see kind of quantitatively here how the error drops as we increase and towards 4 or 5 or 6 dimensions. And we get a stable latent space from this. And so we can visualize it a little bit. So this is just a visualization of the first and second, these 2 latent dimensions, and color coding by some of the original physical properties. So it's fascinating, but also very hard to interpret. I don't know what this beautiful thing is, and what kind of galaxies exactly are represented there, and how. But I think this IRB approach gives us this stable latent space that I think there's some hope in investigating. Okay, and so getting back to the purpose here of trying to really confirm, get further support to this interpretation of the manifold, then what we do is we train this kind of autoencoder just on the fiducial model, no model variations, and then test it on galaxies taken from simulations run with different values of the models. And what we can see is, so here's the fiducial model. It gives us the smallest reconstruction error. And then as we show it galaxies that come from simulations with different values of the parameter, go away from this 0.3 value, we see that the error increases. And this happens for the omega matter variations, as well as for these supernova feedback variations, but it does not happen for the other parameters, which I'm sorry, this is work in progress, so the plot is not great, but the range on this plot here is concentrated just here. So essentially, there's nothing here. Nothing here. So essentially, the reconstruction error of the original properties of the galaxy, the autoencoder, is just as good as on galaxies taken from very crazy simulations with crazy values of sigma 8, again suggesting, I think, corroborating this idea that the manifold, when we change sigma 8, the manifold is not moving, because the autoencoder does just as well encoding those galaxies, but it does not do as well encoding galaxies that come from simulations with different values of omega matter. So yeah, I mean, it's difficult, but I think it's an interesting, forget about these variations, it's just an interesting thing to think about this manifold that we can indirectly discover. Okay, and the third, how long do I have? 10, 15 minutes, good? Yeah, 10, okay. So last, I want to speak about a new suite of simulations that we've been running over the past 6 months or so, and that, again, we will be releasing publicly in just a few weeks. And these are simulations of group or cluster scale halos. So as I said, all the simulations that I discussed so far are in these volumes of 25 megaparsec over age or so. This means the most massive halos we have are about 10 to the 13 solar masses, and even of those, we have just a few. So this means we essentially are limited. We can't really probe the effects of more massive halos on the environment, and those halos are, we do believe, they impart important significant effects on the 10 megaparsec scale that we're interested in. So so we wanted to simulate a new suite focusing on massive halos. The problem is that so there's a technique for that. So that's called zoom-in cosmological simulations. You take cosmological initial conditions, but you make high resolution just in one small region of the box, and then you follow in detail the formation of one halo, one galaxies around it, but the rest of the box doesn't cost you anything. The problem is that to simulate the halos that we don't have access to in these 25 megaparsec boxes. So we want to simulate 10 to the 13, 10 to the 14 solar mass halos, not yet the most massive clusters, but group scale halos. One simulation like that costs computationally about as much as a whole 25 megaparsec box because it's a massive system. So yeah, so we can run 1,000 halos like that, just like we did 1,000 boxes. The problem is that we're only going to get one halo per point, per sampling point in parameter space. So when we measure some properties of that halo, we won't know if this is because of the particular combination of parameters or because of this particular halo, because there's variation, halo to halo variation, sometimes called cosmic variance or sample variance. So we developed a method that I'm quite excited about that can suppress this cosmic variance, and essentially using built-in correlations between samples. Okay, so this is everything that I just said. Okay, so we call this method carpool GP. It's essentially, it's a Gaussian process regression that utilizes the fact that we kind of control how we can create our samples that will serve as the basis for the regression. And in particular, the fundamental thing that we realized we can do here is simulate the same halo, not once, but twice in different points in parameter space. Why is this good? So I think this cartoon should give the general idea. So let's say we have these three halos, three different colors. We simulate all of them at one particular point in parameter space. Now we know that halo 2 is like an average halo. Halo 1 is an overestimated halo for whatever physical quantity we're measuring here. And halo 3 is an underestimated halo. It's just part of the natural scatter of different halos. Now we take the same halo and we simulate it at a different point in parameter space, maybe with different feedback processes, or even with different value of omega matter. We can still take the same phases of the initial conditions to simulate the same system, essentially. And we get this result. Now, essentially, we do something like this. We assume something that is then actually tested during the fit, but the approach relies on the fact that this halo, if it's underestimating this quantity, it will also be underestimating this quantity in some distinct but nearby point in parameter space. So now if at this other point in parameter space, when we measure this value, we know that the average value here is a little bit higher. Similarly, if we measure this value for halo 1, we know that the average value is a little bit lower because this halo is actually a little bit overestimating the average. And once these kind of correlations are built into the kernels of the Gaussian process, we can get a fit that reduces the amount, that gets a less biased estimate everywhere in parameter space. So I'd like to show just with a simple one-dimensional, completely made-up example how this works. So we have the regular situation, no carpool, we just sample 100 points. So okay, so we defined this black line. This is the ground truth function, just completely made up, with some intrinsic noise. Then we sample. We generate samples from this noisy function, and we get these red points. And then we would try to do a Gaussian process regression on these red points to try to get as close as possible to this ground truth. With carpool, now we have only 50 red points. And for each red point, we simulate also a blue point, which has correlated noise with it and sits somewhere on these what we call parameter islands. Okay, so now we're simply going to run normal Gaussian process regression and carpool Gaussian process regression on these two cases. And you can see what this gives us. So this suffers from much more noise, and this really tracks the ground truth much better. And in this particular case, we get something like an improvement of factor of 3 on the noise, which of course corresponds to something like a factor of 10, savings of computational time. Yeah, and we also use active learning. So we start by a small number of simulations and essentially use the Gaussian process to tell us where to simulate next to minimize the overall variance. Okay, so now for real stuff, not for made-up functions. So we did this and simulated almost 700 or so zoom-in simulations with masses between 10 to the 13 and 10 to the 14.5, with a full 28 parameter variations of the TNG model that I described before. Did this Gaussian process, carpool Gaussian process regression. And then luckily, we can test it. We have some ground truth because we have the fiducial TNG model, the big TNG 300 box, one of those flagship simulations I mentioned in the very beginning. It's only at one point in parameter space, but we have, it's such a large volume, we have many samples, so we actually can get something close to the ground truth. We only get it in this one point in parameter space, but the Gaussian process has never seen a simulation, a cluster simulated at the fiducial point in parameter space. It's only seen this kind of random sampling around this large parameter space. And this is the blue line here is what we get with respect to this ground truth from TNG 300 in the black points. So we think this is like a really excellent result. So specifically what this is the YSZ parameter normalized appropriately as a function of the halo mass. So what we see here is essentially kind of the baryons towards the lower mass of the range. The baryons are ejected out of the halos due to AGN feedback. But now what we get is this emulator, not at just at the fiducial point in parameter space, but everywhere in parameter space. And we can do some fun stuff with it. So again, just to kind of give you a visual impression of these are the of how nice this regression works. We have 28 panels here, one for each model parameter that we vary. The points, again, on this YSZ versus mass are the same in all of the panels. They're just color-coded differently. In each panel, they're color-coded by a different simulation parameter. So these are the actual simulations. So now to look at this and say what is the actual underlying trend of this quantity as a function of mass is very hard because each of these points varies all 28 parameters plus has noise. So you say it's largely it looks like a mess, but we get these trends out from the emulator, and then we can see how the YSZ depends on each of those TNG model parameters, and of course, or on combinations thereof. So I won't go into any of these details, but essentially we can do this not only with the SZ Compton Y, but with any other parameter like the quench fraction of galaxies, the black hole mass, and so on. We indeed did that. And in the paper that we'll post in the next couple of weeks, we essentially take just 3 model parameters and investigate in detail through many of these quantities and kind of create a more holistic physical interpretation for how these variations of these parameters affects the physics of the simulation and the state of group scale halos. Okay, so I'll just close here by a bit of outlook. So I discussed these 3 types of simulations: TNG, Simba, Astrid. We're currently accreting more and more groups around the world to join us, and we have simulations ongoing with the Ramses code, with the Enzo code, with the Eagle model, the new generations of Simba, which apparently is called Swimba because it's implementing the Swift code, and so on. And so we want to expand the model parameter space, something I talked about. I tried to motivate. We're also, within each model, we're expanding the number of parameters that we vary, and we want to go to larger cosmic volumes to suppress cosmic variance and to get to probe the larger scales and the larger halos that affect those scales. So these are the kind of where we're investing effort right now. I think the big challenge and sometimes the big elephant in the room is the robustness issue that I talked about, and I think we need to put more effort to address, and hopefully we can address. Okay, so take-home point: I have a growing set of thousands of simulations that sample this multi-high dimensional space of galaxy formation. We show as a proof of concept that information on the cosmological parameters can be extracted from these nonlinear scales that are affected by all the baryon physics processes. And we can essentially marginalize now, to some degree, over all these parameters within the framework of these separate island models, but not yet in between them. And that's that's our challenge here at this point. So thanks a lot for your attention.
Questions? We'll start with graduate students.
So you mentioned the lack of robustness there. What strategies do you think you can employ to address it? Is just throwing more data at the whatever machine learning algorithm you're using, or is there some other way this could be addressed?
Yeah, so I have in mind two approaches now. One is improving our machines, or specifically training our machines to take care of this robustness issue. And I showed one attempt which had limited success, but some success perhaps. And the other is maybe throw more data on it, like you said. So we're accreting more and more of these models. So trying to kind of sample this, get more samples. All we have now is like 2 models don't generalize to a third. We don't know if 5 models generalize to a 6th or not, so to say. And also just trying also something in the same direction of kind of expanding the parameter space that we're sampling. So beyond just taking creating a few more islands in this parameter space, a few more galaxy formation models, try to actually interpolate between the models in the model space. So I have a student now who is working on essentially implementing the Simba galaxy formation model in the AREPA code, which is used for the TNG model. And then we'll essentially make up, so it's completely kind of empirical, make up 20 new parameters that will allow knobs that will allow us to interpolate smoothly in the model space between the TNG model and the Simba model, essentially covering, I hope, some manifold in the high-dimensional model space that open it up. It's completely close to us now between the models. Maybe if we do that in a very general way, we'll actually cover something more general. But
Hi, thanks a bunch. In the field level inference slide, I might have misread that plot, the first one. It looked like the n-body simulations were pretty comparable to the hydrodynamic sims in terms of their ability to constrain omega m and sigma 8. Is that surprising?
Yeah, I think it's not surprising because the dark matter only simulation, the n-body here, so it doesn't have all of that baryonic physics, all of these processes all these other parameters that we're varying, essentially all these feedback parameters. So so it makes sense that once we add all this complexity and all these additional variations, there will be the marginalization will essentially will pay the cost of like getting larger errors. Yeah, but something that is written here, but I didn't say, is actually surprised us initially, is that when we use the baryonic simulations, but take all these channels kind of together, all these different fields together, we can actually get, at least for omega matter, a 2.5% accuracy, which is better than the case of the dark matter only that doesn't have all these processes. And I think the intuitive interpretation of that is that actually by the fact that in this more sophisticated simulation, we can probe all these different things, it's essentially a way to kind of extract more information out of the initial conditions, where essentially, because each of these things is kind of affected by different perhaps features of the initial conditions, something that maybe in the dark matter only case, kind of the information gets erased through the cosmic evolution, but due to the hydrodynamics or whatever other physical processes, some more information is kind of preserved rather than being erased.
Yeah, so you talked about in the cosmology from one galaxy thing, you're kind of using a bunch of different features about the galaxy to infer something like omega. Like, how like robust is that inference to kind of errors in any of those? Because some of those features that you're utilizing are kind of hard to measure in real life. like MGO for
Yeah.
FP is probably not that easy to do.
Yeah.
So,
Yeah.
like how robust is your cosmological inference to like small changes in the more kind of strange parameters?
Yeah, very good question. The answer is very. So, yeah. So it's yeah. So it's very idealized at this point. Yeah. The manifold, if you want, is thin, and yeah, even that come out of even this autoencoder reconstruction that I mentioned, even if we use kind of the full, so a very large latent space that in principle should be able to reconstruct the original properties very well, and indeed it does to kind of percent level. If you use that latent space or reconstructed original space to try to infer omega matter, we already get quite degraded results. Yeah.
Thank you. This is super thought-provoking. And one, I had a question on like your overall framing. So I hate to do all this. I sound like an English professor, I guess. But why did you choose to focus on trying to extract omega matter and sigma A from small scale galaxy simulations when we have at some level other approaches that are rooted in large scales and perhaps more observationally rooted in the actual distribution of matter to nail down omega matter and sigma 8, and then you might be able to marginalize to get some of these nuisance galaxy formation parameters out, et cetera. So why did you choose to approach it this way as opposed to taking the cosmological things as not known, but the best understood pieces and then trying to extract out the galaxy formation from there?
Okay, I appreciate the thought. So yeah, maybe I didn't emphasize enough. I mean, I showed maybe a couple of points that we can actually also infer the parameter values of some of these subgrid parameters. So yes, these can also be useful, but these at this point, as I said, these subgrid parameters are kind of very specific to the model in which, right? So they don't, in some sense, they don't really represent physics in some sense. What we wanted to infer is like these things that do really represent real things like omega matter. And the point is that we think that there are many modes on these small scales. So the classical analysis just, cut at 10 megaparsec or something like that, and just don't bother dealing with biased information, biased due to the baryons. We don't know how much actually information there is on those small scales, but the idea is that more can be extracted if we can account for the baryonic effects.
I have a question. I'll ask you later.
Okay.
So let's thank Shai again.
Thank you.